Welcome to Rust ASMR. We're going to be emulating the noise of a compiler today, but in all seriousness, welcome to Unleash Rust's Potential on AWS. I initially named this talk as AWS is the perfect place to run your Rust projects on, but they told me this sounds better. In any case, I want to introduce AJ. AJ is a staff engineer at Datadog, and him and myself are going to be talking about, well, what are the cool things you can do with Rust on AWS? Yeah. So I'll kick it off. We'll bring AJ later on. AJ's going to talk about how Datadog does amazing things and why is Rust better than Go. Fight us. Okay, let's talk about stuff. Just to introduce myself, I'm a developer advocate, principal developer advocate at AWS. Come from a long, long line of system administrators. Used to program all the way back with Commodore 64 assembly to C to PHP and to like all kinds of modern language. And I settled on Rust a couple of years ago, and I am not going back. So today is all about Rust. We're going to be talking about how Rust works at scale at AWS, how it's a critical element of what we do at AWS. I'm going to talk about how can Rust run anywhere. Things you may not think Rust does, Rust does. We're going to talk about Rust at Datadog, how certain incredibly impressive things Rust does in Datadog's metrics collection and logging. I'm going to show you how it goes really fast on a single thread. And we're going to give you a couple of production tips for all Rust developers. Since this is a silent session, I can't ask you questions directly, but show of hands, who here writes Rust? Okay, the rest of you are about to write Rust. I love that. Love the enthusiasm. Excellent. Let's kick it off. Rust at scale at AWS. Show of hands. Has anybody seen Amazon Aurora DSQL? Couple of you. Excellent. Amazon Aurora DSQL is our serverless distributed SQL database, Postgres-ish compatible. It is made 100% in Rust. It is an active database spread across the world. So it has incredibly high availability, all thanks to, in part, Rust. And I want to talk about how we built this and why did we choose Rust. This project actually started as a 100% JVM project. Java developers building Amazon Aurora DSQL. However, actually they did it in Kotlin, by the way, not Java, Kotlin. However, they were building it, and they ended up with an implementation that's doing roughly 2,000 to 3,000 transactions per second after years of tuning, which doesn't sound that impressive. There were certain limitations they were hitting in with, specifically when it comes to JVMs. Namely, they had issues with garbage collection. So they were hitting the GC garbage collector wall. Basically, they had this huge tail latency because of this. The latency they expected and they wanted to tolerate was 1 second. Because of garbage collection, it ended up being 10 seconds, which is just not a thing you should do. I won't go into the architecture of Amazon Aurora DSQL, but just you want to make sure that it's an incredibly spread out database that's very latency sensitive, especially because writes can happen to multiple points in the world. So the team behind this, a bunch of Kotlin developers decided, you know what? Let's test Rust. Can we implement Rust on this? They've decided to test out Rust on one element. DSQL has multiple different elements of a cluster. One of them is called an adjudicator. Yes. Adjudicator, that's the word. Adjudicator. And they've implemented the adjudicator purely in Rust. Kotlin developers, not Rust developers, decided to implement an adjudicator in Rust. It was 10 times faster. Then the team decided, you know what? Rewrite the whole data plane in Rust. They kept the control plane in Kotlin because best of both worlds, but the whole data plane was written in Rust. However, they realized that was wrong. They couldn't share logic and testing and all those kinds of things between language. So they rewrote the whole control plane again in Rust. Now this project is 100% written in Rust. The team behind it stopped asking, should we use Rust? And they started asking themselves, where else could Rust help? Ultimately, the code ended up being 10 times faster than a Kotlin implementation, despite 0 attempts at optimization. So just pure idiomatic Rust would be 10 times faster than using Kotlin. I'm not saying Kotlin is a bad language. I'm just saying Rust does this thing really, really well. This whole story has a lot more details. If you go to the All Things Distributed blog by Werner Vogels, there's a whole story about this that includes people like Mark Brooker and Nico, all the folks that worked on this project that can give you a lot more than I can do in the next couple of minutes. Suffice it to say, the decision to make such a big, scalable, super fast, serverless database and to use Rust was critical because it makes it go really fast without well, I'm not going to say without requiring skill. Skill is required, but without significant years of optimization, 10 times faster than Kotlin. Amazon Aurora DSQL is not just built with Rust, but it's also built for Rust. So if you folks out there are looking for like a Postgres-compatible database that works really, really fast, works with crates like SQLX, it works perfectly fine. It has certain constraints. I said it's Postgres-ish compatible, no foreign keys and all those things, but our SDK SQLX crate works amazingly with this thing, and it works really, really fast. A couple of things that AWS has when it comes to Rust. BottleRocket, the operating system behind super micro VMs. Firecracker, the micro VM, all of those things are built and written in Rust years ago. So the places we're looking for performance, the places we're looking to make stuff really fast, secure, fearless concurrency, we use Rust. I was given the permission to say that any data plane project in AWS right now, by default, uses Rust. Also, we built an MCP server this week, I think. Yes, the MCP server called IAM Policy Autopilot is also built in Rust. The MCP server plus the command line tool that does all the magic is also built in Rust. What I'm trying to say is Rust can run everywhere. It's not just built for big backend systems, it's also built for your MCP servers, your command line tools, but also your Lambda functions. Cargo Lambda is a wonderful community project made by David. Yes, David. I forgot the gentleman's name. I'm sorry, David. David built a tool that helps you deploy and manage and run and orchestrate Lambda functions built in Rust. Actually, just recently, I think it was last week or 2 weeks ago, the Rust support for Lambda went GA. However, I've been writing Rust Lambda functions for a couple of years now, so even though it wasn't generally available, it was still incredibly powerful. So with tools like Cargo Lambda, that's the only thing it takes for you to deploy. Create a new Lambda function, an HTTP Lambda function, start it locally, invoke it with an example API gateway request. You can build it, and you can also deploy it. Fantastic, wonderful. All built by the community, all fitting in the same cargo-ish development ecosystem that Rust is so famous for. But would you deploy a Lambda function like this? No? No, of course. How would you do it? You don't have to say microphones, all that stuff. Infrastructure as code, right? Cargo Lambda supports CDK. If you use the Cloud Development Kit, if you use even Serverless Application Manager, or SAM, you can use Cargo Lambda to deploy serverless application straight from your infrastructure as code. There's a specific L2 construct here called Cargo Lambda. It has a type called Rust function. You just point it to your cargo.toml, and away it goes. Like your any old Lambda function. There's no specific runtime, by the way. The Rust Lambda functions use just your generic Amazon Linux 2023 runtime. Works amazing. But you know what also Rust can do? Can Rust do front end? Kinda, right? Well, it can. Rust plus Lambda plus HTMX. Anybody here use HTMX? Oh my God, let me awaken your PHP nightmares. It looks like PHP. I built a thing, a link shortener in Rust with oh my God, with Lambda and HTMX. So I have a whole stack here, from a static website to a database to a bunch of Lambda functions that do the whole thing. There's almost, well, I'm beyond HTMX, there's no JavaScript involved. And it's all possible with Rust. Let me show you. I can show you this thing in action. If I open up this thing and switch to a demo, that is my link shortener. There's no authentication, so please be gentle. You can post any links there. It's public. All of these links are accessible. But I can come here, copy a link, drop it in here, hit shorten, and in a second, it's there. It's done. That's all Rust. The little green box you see, that's HTMX. HTMX works in a same way, well, in a similar way like PHP used to work. You make an AJAX call to the backend. The backend, a Lambda function, produces HTML using a templating engine and returns pure HTML and positions it on the screen. Wonderful. So you can do that. It's not as cool looking as React or something like that, but for all of us folks that actually love to use REST APIs the way they should have been used, as using hypermedia as the engine of state, Rust plus HTMX helps you out a lot. Let me show you some code. This is an entry point of a Lambda function written in Rust. It's a main function that has some extraction of environment variables, SDK configurations, so like DynamoDB here, and just invoking the specific, well, running the specific function here from a function handler. That is a function handler. Like any other Lambda function, it's a normal function handler, a synchronous function in this case, that does a lot of stuff. But what's beautiful about this, why is it really cool? It has type safety in its events. Yes, of course, it can get just any old JSON, but it can be very type safe what it gets inside of that JSON. So, like any other Lambda function, just way, way faster. I'm going to go and switch to my code a little bit more so I can show you how these things actually work. So if I go here, here's another Lambda function. It's one from the same project, but in this case, this Lambda function takes an event from Kinesis. Yes, Kinesis. This Lambda function is triggered by Kinesis. As you can see here, it uses a Lambda event called a Kinesis event, which is, again, its own special type. Wonderful. It has its own special payload, and the payload in this case is a Kinesis event, which has specific types of records called Kinesis event records. Amazing. I take that data, and with the speed of Rust, I decode that data. Fun fact, if you ever use CloudFront and stream your real-time logs into Kinesis, you're streaming something in the format of TSV, tab separated values. I had a whole discussion with people, why TSV, why not CSV, why not JSON? I don't know. We can discuss that later on. I'm taking all that data, I am putting it inside of a struct, and I'm basically writing it somewhere else. That's it. Simple as that, works really fast, compiles to a binary, gets shipped over to a Lambda function. So why should you care about Lambda functions and Rust? Why should you go ahead and ditch Python and JavaScript and whatever else you write your Lambda functions in? That's why. Cold start, 1.2 seconds. Warm start, 4 milliseconds. Barely any memory. 29 megabytes of memory used for a Lambda function. Incredibly performant. Currently, the only faster Lambda function runtime is C++, but by only a fraction. This works great on ARM, on x86, doesn't matter. I think ARM, there was a recent, somebody did a whole wonderful rundown of the speeds of different Lambda functions. Rust on ARM is faster than Rust on x86. So there you go. Really, really fast. Also a slightly lukewarm take. I said this on my previous session, but I think we should all stop writing Python. Hear me out? Hear me out. In the world of large language models, in the world of coding assistants, it makes you perform so much faster if you have a language that's being produced by an LLM that can be immediately compiled, tested, and just, there's no runtime errors. Well, there are, but they're much rarer in a compiled language, in a type-safe language, such as Rust. So if you are still using an LLM to generate Python, think about it. Can you do this thing, the same thing that you want in Rust? If the answer is yes, you're going to have way faster development life cycles. Speaking of Rust and serverless and fast, I'm going to hand it over to AJ here, where he's going to talk to you all about how this thing is being done inside of Datadog and how, well, Datadog makes Rust go really fast on AWS. So AJ, come on here. Here you go. Good luck.
Hey everyone, thanks for joining us here at the end of the conference. I know it's been a long week, and hey everybody on YouTube. My name is AJ Stuyvenberg. As Darko said, I'm a staff engineer at Datadog. I'm also an AWS hero. I'm really excited to talk through all of the different ways that we're using Rust at Datadog and how I think we're trying to kind of expand that to more and more use cases. So there are kind of three main verticals where we're using Rust here at Datadog today in production. The first is serverless. We're using it to replace our legacy Go Lambda extension with a Rust version that's built for purpose. The second is in our actual Datadog agent itself, where we're taking a look at our agent that we deploy into customer infrastructure as a separation between the control plane and the data plane, and we're rewriting part of the data plane components in Rust. And finally, in our backend, in our distributed systems, where we're using Rust to power our time series data systems. So first off, serverless. If you're brand new and you've not used Lambda before, first off, I would suggest, as Darko said, try out Cargo Lambda. It's so easy. It's like 1 or 2 commands. You can have a Lambda function running. But serverless components and serverless functions on top of AWS are a little weird. They behave a lot more different than you would expect if you're coming from a traditional kind of EC2 instance background. The Lambda functions themselves are not long-running processes. Lambda will schedule your function to run when it receives an invocation. It will run until that request is finished, and then it will send the data back to the user. For the longest time, this did not leave very much room for telemetry providers to do asynchronous flushing of logs and metrics, and all sorts of other things, traces, profilers. That all had to be done synchronously, or it had to be serialized out as logs, and then it had to be read asynchronously at the end. That was really painful, it was very expensive, and through some time we were able to lobby AWS to build out the extensions API. This allows you to do async processing inside of Lambda. And the way this works is it divorces the Lambda function handler call from the actual throttling of the CPU, and it allows the extension to kind of run after the function call completes. In most cases, we're running concurrently, and I'll get to that. There's some incredible performance gains you can get out of that. But there are kind of 3 main points when you're looking at building an extension for Lambda. It's fraught with risk because the extension acts as a parent process of the application. This means that if your extension ever dies, the sandbox, the handler code that is also running alongside it through no fault of its own will be killed immediately. This is one of the biggest reasons we were advocating for a move from Go to Rust, because we never wanted to be in a situation where a memory erase condition caused us to crash the customer's handler function. The other aspect is that each Lambda sandbox can process 1 serial request at a time in on-demand mode. Now today or this week they launched Lambda managed instances where these are now multi-concurrent. But for the breadth of the time of Lambda, each sandbox can run 1 serial request, and it can run them many over and over and over again until the sandbox is reaped. They each have their own extension process. This is very different than the way that Datadog agents have behaved in the past, where they tend to be subscribed to multiple other hosts, or maybe you'll run one Datadog agent scheduled in a pod alongside of many, many application agents all sending data to it, where the Datadog agent would have to act as like a load balancer. And when Lambda first announced extensions, what we did was we ported our Go-based Datadog agent over to a Lambda extension. And that got us out the door quickly, but it had some problems. You're looking at a graph of the cold start time or initialization duration from a baseline to our initial Go agent implementation. This was between 700 and 800 milliseconds, which is an incredible overhead for people to stomach when they're moving to serverless and they want observability. That was a lot. I'm not going to lie. It was untenable. And what we were able to do internally is make the case that this process that we've been doing of taking our existing agent, retooling it in Go, retooling it to be used in serverless was approaching untenability. What you're not seeing here is that many, many, many weeks and months of effort went into paring down the build that we actually made for serverless from the main Go agent so that it fit within the constraints of Lambda. The binary size was quite large. The initialization time was quite high. There are a lot of init functions that are being called in Go code. And fundamentally, we got to a wall where we were trying to use Go plugins, which are just not that mature, and they're really not well supported. And we realized we had to make a change. When you take that in concert with the need to have a as crash-proof as possible system that we deploy alongside Lambda functions, because again, they act as a parent process of the function, we knew we had to make a change, and we had to switch over to Rust. Over about the period of about 6 months, myself and a small team of people who had never written Rust before built out a new version, which we codenamed BottleCap, and we rolled it out. We were able to get a graph that looks a lot like this. This is the cold start duration across all of the supported runtimes we had, where you can see we're going from like 400 to 500 milliseconds of overhead down to about 80 milliseconds of cold start overhead by switching over to the Rust implementation. We did this live. We did this by deploying both the Go agent and the Rust agent in parallel in the same package, in the same zip, which is how Lambda extensions are processed. They're packaged as Lambda layers. And what we would do was we would boot the Rust agent, which didn't fully have all of the support that the Go agent had. We would auto-detect the customer's configuration, and we would find gaps in places that we were missing where we knew we hadn't supported it yet. Some of the more complicated features like our security and AAP process for application security weren't yet supported, and we were able to fail over to the Go process when we needed to. And over the period of a couple of months, we whittled away at those cases, and we finally got to the place where a couple of months ago, we were able to delete all of that code. Now, Rust also helps us optimize even further than just the cold start time. What you're looking at on this graph is the post-runtime duration of a Lambda function. What this metric is tracking is the amount of time after your handler finishes where extensions are still running. In this case, the only extension registered is Datadog. What you're seeing is our next generation extension before and after. And what we started doing was we realized we were able to trick the runtime and cheat death. So we would begin by working with our intake team to ensure that the TCP keep alive on our intakes were long enough that they would outlive, the TCP connection would outlive a Lambda sandbox lifecycle, which is not published, but it tends to be a few hours, and then after the last invocation, about 7 to 10 minutes after the last invocation, it'll shut down. So we knew as long as we had enough coverage there, we would be able to resume that TCP stream at any time without dropping any data. So we very carefully reworked our flushing strategy that when at a fast enough state, when you are running maybe steady state and you have many invocations coming in, we predict that that will kind of continue. We'll start flushing data and then signaling to the Lambda runtime that we're done, even though we're not. And in a hot Lambda function, it will almost immediately receive another invocation. And as a result, that TCP stream is basically unbroken. And we went from, this is a maximum chart. It's not P99, it's max. We were able to go from between 60 to 140 milliseconds of max down to about 500 microseconds. This makes Datadog run with almost no overhead in terms of sending data back to Datadog in your Lambda functions. But that's not all. Once we were done, I had the immense pleasure of approving this PR from one of my teammates. It required like 18 reviews, but 53,000 lines of Go code were removed from our Go agent after this time. And that was mostly a function of all the adaptability we had to kind of bolt on to our Go agent to make it work inside of a Lambda runtime. But let's talk some more about the Datadog agent itself and how we run on top of, outside of a serverless workload. We'll kind of switch gears. We're going back to a world of long-running processes and large instances with a lot of memory, a lot of CPU. Datadog's agent acts as a collector and a probe system for lots of data coming out of your customer workloads and sending back to Datadog. There's a lot of components here, and the one we're looking at rewriting is kind of the core agent, the metrics data plane action part of our application, where metrics are being collected by the agent, they're being aggregated, they're being counted, and they're being sent back to Datadog. Other components of the agent include things like reading configuration files, setting up proxy connections, understanding how the user wants the system to be configured. That's all still in Go, but what we've been working on is having an experimental project for unbounded user-based telemetry data flowing through a very efficient Rust data plane, which is in this kind of core agent component. We've been rolling it out internally, and we have seen some pretty incredible results, including a straight 25% reduction in CPU per pod when switching over from the Go agent to the Rust agent data plane project, and about a 33% reduction in memory. This is, again, we were doing this 50-50 pattern, right? Trying both of these systems out in parallel in our own production clusters. And what we were seeing is that there's such an amazing reduction here, we wanted to kind of roll this out. So what we were able to realize is that there is this symbiotic relationship with the core agent on the Go side, just because metrics are time series data with a timestamp, which is usually 64 bits, a point, which is typically, we kind of store it as 64 bits. You can go bigger or smaller. Then a set of tags, which are key value pairs. And those can get really, really long. Those can get unbounded. So metrics data systems tend to be allocation factories. They tend to create many, many little allocations over and over and over again. You can get some performance out of Go doing off-heap stuff, and I'll talk about that in a second. But for the most part, it's very, very hard to make that work with Go's memory management, and Go's world tends to kind of creep up and up and up as the allocations increase and the rate of them increase. So Rust has been really useful for that. But let's talk about Datadog's backend. If you haven't heard of us or what we do by this point in the talk, we're running a very, very large distributed backend. We're operating at the scale of trillions of data points every single day. A huge part of that work is splitting things, partitioning, and sharding things to the point where a core can get some amount of useful work done. Historically, that had been done in Go, but we had found that especially on the metric side of things, these allocation-like factories that I was describing become really painful, and we're spending about 30% of our time in garbage collection that you just cannot erase. So I want to talk about Monocle. Monocle, under the hood, it's an LSM tree architecture. So if you're familiar with RocksDB, or you're familiar with, I think even like Dynamo has some aspect of this on the indexing side, effectively what we're doing here is we're creating in-memory memtable, and periodically as that fills up, flushing that to local disk at different levels, and then a background task then compacts these tables into larger and larger tables. Eventually, those do get written off into blob storage, like S3. So recent writes are buffered in this in-memory data structure, and frequently accessed data is served from this in-memory cache. Then on disk, it's stored in a custom format, similar to static sorted tables. It's organized and it's indexed, and it's all time series data, so it's optimized for time series lookups. Then that background compaction process is reorganizing those data over time, and it's handling rewrites, because very often what we'll get is some subset of points for a timestamp, and then we'll get another set of points coming in later, so then we'll aggregate those and rewrite that over and over and over again. Here's the architecture of the system in a production environment. What we are running here is a large fleet of nodes that are each reading from Kafka partitions. Each of those runs an intake task. And we're running a very, very standard thread per core architecture per partition. Each of those are then running a copy of our storage engine per each core. And when we were ready to roll this out to production, we knew that we had kind of two problems we had to solve. The first was how to do it safely, and the second was how to make sure we were doing it right, and we knew that things were successful. And the challenge with this whole system, really, and what Monocle powers, is that distributed LSM tree systems have to serve both reads and writes. In a lot of distributed systems, what you try to do is disaggregate the reading and the writing into different cores and different CPUs. And that is really nice. It gives you a lot of nice properties. But when you're querying metrics, when you're sending metrics to Datadog, you want to kind of write your data and read it right away, especially for monitor alerting, right? If you think about a time series metric of data points for your system that you're monitoring, like CPU or Kafka lag or something like throughput, and that value goes from some large number like a million requests per second down to 0, or it goes from 0 to 1,000,000, those are things you want to know about as soon as you possibly can. So we have to both build a system that is serving many, many index requests per second, and then also make that data queryable. So we started rolling this out, and on the left you can see kind of the previous gen data, right? You can see the Rust side. And the Go side was serving traffic until we hit a pretty large spike. And we went up to 40 to 50K points per second, which is up from about 5,000 points per second. Now, as I said, this system, this service is also serving its own reads. So you can see on the bottom set of slides, on the left and the right, we're looking at the queries per second that pod is serving. And these are all per pod. But what I want to point out is that while the curves look similar, the scale has changed significantly. And on the Go side, we were running at 60,000 points per second per pod. We started dropping queries, and the service could no longer serve query traffic. But the Rust side was able to actually absorb that load and start running more and more queries per second, while it jumped all the way up to 3.5 million requests per second. 3.5 million points per second per pod, which was 60 times greater. And it just kind of absorbed that and ate that up. So I want to talk about some other places where Go can be considered an inferior runtime for really, really high volume and high scale operations. And one thing we do a lot, which has shifted a little bit here, is tags. We group tags. So this method call is you're going to receive an array of tags, and then you're going to receive a set of tags to group by, and you want to return the values for those tags. Let's look at the actual code. The Rust code is pretty idiomatic, pretty simple. We have a little helper method called asGroup. We call that on line 9, so we'll look at key. We receive this array of tags and this array of groups, and we return a string. So we create this key tags variable, this vector that we're going to append to. And for every tag in the tags, and then for every group in the group, if the tag has that group, we're going to push the keys onto that tags array, or that tags vector. At the very end, we sort them, we dedupe them, and we join them, and we return that. Very, very simple, very idiomatic. The Go code looks the same, actually. It's just fine, right? Same roughly 17 lines. Same thing, we have this helper method has key. That's just going to look to see if you have that key of the prefix of the colon and it's there. If it is, return true. Same thing. The problem is that at scale, this is an allocation factory. And continuing to append to those slices in Go will reallocate that vector over and over again. Rust can do the same thing, but if you're using something like gemalloc, you can create many allocations ahead of time and get some kind of advantages there. And we found, just straight up, no gemalloc, nothing, that the Rust code is almost 3x faster on a C7i XL. And I think Darko wants to pop up here and ask me a question quick.
I just want to, so he mentioned that how, can you all hear me? Yes, okay. He mentioned how you move from Go to Rust,
Correct,
right?
yeah.
So one of the things that I've heard from developers is like, so you have a bunch of Go developers.
We do.
All of a sudden decide to write something that's not garbage collected, has whole different memory type of management.
Yeah.
Was that a challenge? Or like, how did these people kind of adopt it, and why did you decide to go? And I see that you can get similar speed sometimes with Go, but...
You totally can. So I want to address that. There's like an elephant in the room here, which is, you don't have to use Go's garbage collector. You could write off-heap data structures in Go, and we did. And we did have a service that sort of used something like Monocle. It was actually using RocksDB, I think. That did a ton of off-heap memory management in Go. And when we decided to move to Rust, we didn't see a ton of huge performance gains, but what we did see was that new developers were able to pick up the Rust code much more simply than they could with the off-heap Go code, because what happened with the Go code is that it became kind of an unmaintainable mess that nobody wanted to really touch. Everyone was a little afraid of. And that tends to happen if you start to do off the trail things with different programming languages. They tend to be very difficult to maintain, and people kind of don't want to touch it. And that brings me to my last point before I hand things back over to Darko. Idiomatic Rust code tends to yield the performance of what very carefully optimized Go code does. I think this is the key takeaway for stakeholders and people in your organization if you're thinking about this. If performance is a feature and an aspect of your system that really matters to you, or cost really matters in terms of fully utilizing the compute you're paying AWS for, I think it is very simple to write Rust code that right out of the box is very good. That would take you a very long time to get there with Go. With that, I'll hand it back to Darko.
Thank you, AJ. AJ's going to be back as well. He's not going anywhere. So I'm going to be talking to you a little bit more about, you've seen how Rust can do fast. It can really be fast, especially when it comes to incredibly big distributed systems like Datadog. I'm going to show you certain things of Rust that actually, how you can make it so fast working with AWS. I'll give you just a little example. I'll show you some code and explain a little bit of the code, but that's not the entire picture. I'll show you how it can go really, really fast doing something like processing CSV files. So I have an application, it's a demo application that does the following. I have 10,000 CSV files in an S3 bucket. Each one of those CSV files contains 100 lines of data. They're not huge CSV files, but they contain data. In this case, it's some sort of weather monitoring data, right? My application does the following. It lists all of the buckets, all of the objects in an S3 bucket. It downloads all of them and serializes them into structs. And then later on, it stores them into DynamoDB. What you see here is me using things like streams, like semaphores, like task buffers to do all of this incredibly fast. Going back to this, the whole list 10,000 objects and download 10,000 objects and serialize them into their own structs takes 9 seconds on my laptop in my hotel room. Incredibly fast. But then when it comes to writing to DynamoDB, it does it so fast that I can write 1 million records in around a minute. Let me show you all of that. So I'm going to first show you something. I'm going to talk about a concept of a semaphore and a task buffer. Now, when I was a wee little developer, concept of a semaphore and task buffer seemed very complex to me. And it is a complex topic, but Rust, idiomatic Rust, makes it so easy to do. Let me show you how this works. In essence, you're using semaphores and task buffers to control the flow of your application, to control the amount of tasks and processes you are running so you don't end up throttling something in the back. In this case, I have 500 tasks spin up with a task buffer. And each of those tasks gets a permit from the semaphore. The permit allows the task to call S3. As soon as it has called S3, it drops the permit and another task can pick it up so it can make an S3 call. Why is it doing this way? Because I don't want to hammer my S3 endpoint so I get throttled. I will talk about throttling in a second, but this is a very neat way for you to control the amount of data, amount of speed that Rust is actually doing. So I'll switch over to my thing here, and I'll show you some code. Is this it? It's not it. It's, let's see, where's my code? Is it this one? Okay. So here, let me show you a couple of things. So this is my function that downloads files and processes them into structs. I have a semaphore of 500 permits. I get all the results. The results in this case, sorry, I get all the records. I create records from CSV keys. And CSV keys are just a list of files that I ran in the first instance. I start processing them in a stream. I clone the semaphore and I create an asynchronous task using async move. Each of those asynchronous tasks picks up a permit. This is what it gets from the semaphore. It gets a permit, says, yep, I can do my task, I get the permit. It does a bunch of S3 calls, does a bunch of conversions into a struct, and once it's done, as soon as the async move block is done, it returns the permit back, and that permit goes to the next task. The buffer unordered 1000 gives me a list of 1000 tasks. These tasks are queued up, they get their permits, only 500 of them get permits, and they run. In my example, this doesn't make a lot of sense because it's just a bunch of S3 calls. But if I had additional processing here, like something up front, some other things that are CPU bound instead of IO bound, like a network bound here, it would make sense to have a bigger task list so you can kind of buffer up a bunch of stuff and then give them out permits to do stuff on using S3 API calls. And this makes it incredibly fast. I download and process these files, as I said, in 9.8 seconds. And that is, the only thing I'm bound here with is the speed of my internet. So that is one example of doing this. And remember, this is all running on a single thread. This is not multi-threading yet. This is literally idiomatic Rust using the crate called Tokio, and its semaphore feature. Nothing special beyond that. However, what is special is the following function. I have a function that writes stuff to DynamoDB. Once I get all those records, I write them to DynamoDB. And I have a function with just your standard backpressure. Backpressure is basically just using exponential backoff and throttle handling, so I don't overwhelm my DynamoDB. So if I get throttled, I wait for a second, I try again, if I wait again, right? It's just super simple. It has a bunch of retries. If it fails after 10 retries, it fails altogether. Let me show you this code. There we go. Write to DynamoDB with backpressure. Again, in this case, I'm actually not using semaphores at all because that's the only thing I'm doing here. I am exclusively using just the task buffer. So I'm, again, like before, taking all the records that I got from the previous function, I'm putting it in a stream, iterating over them, and spinning off an async move. I try to write stuff to DynamoDB. The match DynamoDB basically attempts to set the item, some record in a DynamoDB table. And then, if it's OK, I move on. Perfect. The little PB stuff you're seeing, that's just a progress bar, so I'll show it to you in a second. Don't ignore that, but OK, return, we're fine. Record has been written, the async task is done. But if it's not OK, if it detects a throttling error, and if there's retries less than 10, add 1 to the retry, add it to the retry count, and wait. There's a little delay, and it's exponential because it uses basically the number of retries as a multiplier for the duration of the wait. That's called exponential backoff. You're just increasing the amount of time you're backing off so you would handle throttling that much better. Then you just add a Tokio sleep for the amount of delay you want and try again. If we went over 10 retries, fail. That's it, fail to write the thing. And to be honest, this works, right? I have 1,000 tasks. What happens here is 1,000 write attempts at the same time try to happen. Hopefully they're not throttled and they all complete. All running on a single thread, on a single core. But we can do better. We can do, again, using idiomatic Rust, with just the Tokio crate, we can do adaptive backpressure. Adaptive backpressure actually does the same amount of, it does the same like before, it has exponential backoff. However, it uses permits, it uses semaphores to control the amount of requests that are actually going there. So in this example, if I'm throttled, I remove 10% of permits. I say, whoop, let's slow down. We cannot handle this much traffic. Remove 10% of permits and try again. If I notice that I get 200 consecutive successful writes, I add 10 permits, right? And then if there's again throttling, I remove 10%. If there's 200 more, I add it up. Why is this? Why am I doing this whole thing? Remember, we're working with the cloud. We're working with cloud systems. In this case, it's DynamoDB, but it can be any backend system. Doesn't really matter. But DynamoDB and other cloud-based backend systems scale, right? So let's say you have a system that detects a lot of traffic and starts scaling. Before it starts scaling, you want to give it some time. And as it scales out and you get more successes, all of a sudden there's no need for you to throttle anymore. And it just goes full blast. So this gives your backend systems the ability to scale in due time, and well, it recovers back to the appropriate speed that you want it to do it. Let me show you how the code looks like. It's a very similar function in this case. My adapted, my permits number is set to 500. So in this case, again, I have a semaphore and I have a task buffer. But let me show you the function. It all looks the same. There's an async move thing. It picks up the permit in this case. And it tries to write something to DynamoDB. If it succeeds, perfect, adds 1 plus to the consecutive successes number, to the consecutive successes arc. And if streak is over 200 and active permits is less than 500 in this case, or the adaptive semaphore, it adds 10. This is the adaptive part. This is where we add stuff to it. But if we get throttled, we add to the retries. Basically, this is where we start reducing the amount of permits, right? We basically start adding to the number of retries just so we can show it out. But if the current amount of permits is bigger than 500, then we just basically remove 10% of permits. That's it. And then we wait the appropriate amount of time thanks to the amount of retries and exponential backoff. Works exactly the same, but with a lot more smartness to it. So let me show you this thing in action. I have a DynamoDB table here. Now, it's a normal pay-per-request DynamoDB table. So that's what we like to call the on-demand pricing. So by default, when you create an on-demand pricing database, you get 10,000 read capacity units and 4,000 write capacity units. Sorry, that's 10,000 reads per second and 4,000 writes per second. So let me show you. This is running on an EC2 instance. It doesn't matter what EC2 instance. It's running on a single core. But it's running on an EC2 instance in a single core at 500 permits. Well, that's the semaphore, right? So if I do cargo run, release, and run it, that's the file download speed, 10,000 files in whatever seconds that was. But look at the throttling. Even on a single core, on an EC2 instance, I'm getting throttled like crazy. I have 5,000 throttles. My permits went down below 50 because the application detected, okay, I'm just gonna start slowing down so I don't just keep on throttling here. I'm gonna slow down, and as soon as the DynamoDB table scales up, it's gonna start doing it. It's gonna increase the number of permits. Now, unfortunately, this is gonna finish way faster than the DynamoDB table scales up. So I can't really show it to you in action, but as the DynamoDB table scales up, as there's less and less throttling, the number of permits grows, and the speed of writing also grows with it. So when you're designing backend systems that are scaling up, make sure to scale up in significant chunks. Scale up like DynamoDB by 50%, right? Or actually, it scales up by 100%. It doubles the write capacity units when it starts scaling up. But this is a good example of Rust doing this thing on a single thread, on an EC2 instance, and it just completely flooded my DynamoDB table. That's your pay-as-you-go. Now, there's one more way. AJ, come here. There's one more way you can make this work. We don't have an example of this, but AJ is going to tell us about how Rust can do this also with the same crates, with Tokayo, but you can do this in parallel. So tell us a little bit about that.
Yeah, absolutely. I want to talk a little bit about the ergonomics of Rust in parallel at scale. Tokayo is kind of the default asynchronous runtime crate. If you're a Node programmer or .NET, you're probably familiar with like the event loop kind of style, or green threads or NM threads. The idea is that the runtime threading will, the runtime will schedule tasks, and instead of doing kernel space threading where you have to incur a kernel mode switch every time you want to switch between different concurrent tasks, the runtime will manage it for you. Tokayo will manage it for you. Most of the crates you're going to use when you interact with, especially AWS's SDK, Cargo Lambda, and a lot of the kind of popular crates that you can use to kind of talk to different SDKs or different libraries are going to be Tokayo based. Especially if you're a Lambda developer, I find Tokio to be really pragmatic because it helps run more than one thing at one time when you have only one core, which you often do inside of Lambda. So I was just commenting on Darko's code before we gave this talk. The join set is a very popular option here. You can also use a join set which spawns off tasks and feed that by a multiple producer single consumer queue, or even just a simple queue that will have a buffer limit. So you're able to kind of take off chunks of task at a time, and if there's no available room, if that buffer is completely full, you'll kind of get some back pressure. So if you're brand new to Rust, that was kind of my little spiel there. I think we have a few more production tips too we want to go over.
Yes, I just want to show you, I'm running this again on a provisioned database. This has 12,000 write requests per second, and it's not getting throttled.
So here's where you'd want to be using something like a join set, where you could maximally saturate and make Dynamo your bottleneck again, which is something I occasionally enjoy doing from time to time.
Exactly, yeah, exactly. So like in the previous example, I got throttled. In this case, I'm not. Now I could potentially scale up my number of semaphores, my permits, but doing multi-threaded here would make a lot more sense.
And Tokio manages that for you. One thing that I really want to call out is all the code Darko showed did not have a lot of the scary Rust bits I think people see in tutorials. There were no lifetimes here. The borrow checker wasn't complaining about anything. The code looked, for the most part, like pretty idiomatic code that you'd kind of read if you were thinking about pseudocode. Maybe the async move and the errors and the matching is a little different, but for the most part, it looks like a typed language. This follows Rust primitive of RAII, which other languages have, of course. Resource acquisition is initialization. So memory is allocated by malloc. In this case, I don't think you're using another allocator. It's allocated by malloc when the closure begins, and then when it ends, it's freed. And for the most part, that can get you really, really, really far. That's why I want to get into production tips, because one thing you should do is run a profiler. This is not an observability talk, but I am an observability fan. So before you go into production, I do want you to go off and run your program under a profiler. It will tell you where the CPU is spending time. For the most part, it should look like you expect, and what that kind of process is designed to do is to ensure that you don't see any surprises in the way. In our case, I did find some time in lock intention that I wasn't expecting, and we just kind of moved to like a lock-free data structure. LLMs are very helpful here. One part when I was working on our low latency Rust Lambda extension was I knew that we needed to switch our stats aggregator from a lock-based implementation to lock-free, and I had kind of two ideas that I could do. The first was, well, I could just create two aggregators and then atomically swap between them. And then one of them could be running and flushing data while the other one is receiving new writes, right? That would work just fine. I could also use PSCs or channels to receive data and then kind of have a tombstone event come through or like a flush event come through and mark when I wanted to flush everything. And then I could kind of stop reading from that queue. Data could still build up and it could then aggregate and flush the data. Both of those were good options. In a different world, I would have picked one and just did it. I was able to make ChatGPT just go ahead and build both of them, benchmark them with a Rust crate called Criterion, pick the fastest one, and moved on.
Exactly. Okay, let's talk about production tips.
Yeah.
So a couple of things here. We're close to the end, so let's talk about a couple of things. I think the first ones are...
if you're moving into production, into your first Rust program, you really use Clippy. It's a linter and formatter. Lint away the unwraps. Unwrap, if you haven't heard of this, you should have in the last couple of weeks. What unwrap will do is if you give it it's a result element that result method that you call. If you have a successful result, it continues on. If you don't, it panics and crashes the program. This is not something you want to happen unless you truly cannot continue. So Clippy provides really, really good linting options to disallow any unwraps or expecs everywhere. It's very easy to write, and once you set that up, you should treat these warnings like failures. That kind of sucks because if you remember the first time you saw like a C++ compiler or Clang throwback 3,000 warnings of your code and you still ran it, you're like, yeah. I'll fix those later.
Yeah, exactly.
Just do those early. That's my first recommendation.
You can use unwrap when you're developing. It makes you move fast, but do not forget to remove them. That's kind of the thing.
And LLMs do like to throw them in there.
Oh, I love them.
That's one of the reasons I like them to be linted away, because if you're using like a Claude Code or an open code, which I prefer, it will check and catch that before it commits, and you run them, and then it will say, oh, I have to remove this, no problem, and it will do that for you. The next thing, Tokio programs, big fan. Monitor the metrics for blocking tasks. There's a metrics crate for this. You want to make sure that you're not blocking the runtime from proceeding. The way this works is that Tokio will move to a new task any point your program has an await call. So what you can imagine happening is you have like an API call, .await, so you're waiting for HTTP response, and then that can do other work. That's great. Sometimes people will do that and then do something like, I don't know, compute 10,000 metrics, and that will completely saturate the core for the full time, and you may want to be able to share that. For those tasks, or if you're like doing encoding or something, use spawn blocking. That is a separate thread pool for tasks that can block the runtime, and then Tokio does a little bit different sharing, cooperative sharing for that. In Lambda especially, you don't have as great of access to things like Tokio Console, which is a web tool that will let you debug a running Tokio program. There are kind of two ways to get around this, especially in Lambda. The first thing you can do is you can reach into the Tokio runtime runtime module, which has like a stats dump feature. This is really useful. It will tell you which tasks are waiting for scheduling time and which tasks are dominating the scheduling time. So if you're like me and you're looking for a needle in the haystack of a bunch of tasks that are taking too long, that is a great tool. You can print it right to standard out. The second option in Lambda is you can run the Lambda runtime emulator on a Linux box and run a profiler. And that is also something you should just do anyway. But that will also allow you to run Tokio Console, which will allow you to connect to it and see the web UI for the task metadata that Tokio provides. It's really, really useful. And I think it's a super important step before you go into production.
Once you start building with Rust, you will notice how fast it is. Again, even just pure idiomatic Rust just makes stuff go fast. And this is where you start going into the weeds of like, can I make this even faster? Is there some sort of a process block? Should I use perp? And like, you're just gonna get all of those things out there. Flame graphs are your friends in this case, so for sure. For things that requires a little bit more and task management and parallel stuff, use semaphores, use task buffers. They will definitely help you achieve stuff like that. I could have had just a loop on doing stuff like that, but it would be way slower than me just spinning up a bunch of tasks like that. So definitely consider, even though they tend to sound a little bit scary, once you get a good hang of it, it just moves really, really fast. Lastly, when working with SDKs, specifically like an AWS SDK, please parse the SDK errors. AWS SDKs are really good when it comes to errors, and I'm going to give you an example of this application. I actually work with, I have a little function here at the beginning that parses my SDK error. Basically what I do is I pass an SDK error type to this function, the put item error specifically, and it checks, is the error a service error? If it is a service error, is it provision throughput exceeded exception? Is request limit? So all of those things are nicely documented in the AWS Rust SDK, and then based off of those errors, you can do a lot more application management, in this case, throttling and whatnot. I guess that's it, right?
Yeah.
The last thing I guess you all have for you is to Rust up, install Rust, cargo new your favorite pet project, and again, start building with Rust on AWS.
And have fun.
And have fun, yes. Thank you so much.
Thank you.
We're going to be here for questions if you have. Feel free to ask us. Both AJ and I are active on social media, so you can find us on LinkedIn and whatever other stuff exists. We share a lot of content on Rust, both of us, so if you want to learn more, definitely don't be afraid to reach out.
Yeah, cool, thanks.
Thank you all.